Welcome to Lecture 2 of Physics 506. In this lecture, we're going to tell you about the 5 critical operator identities that you need to use to do just about everything in quantum mechanics. And some of these operators are relatively easy to derive, like the Leibniz rule, which is the product rule for commutators, and the Hadamard lemma. The exponential reordering identity is very closely related to the Hadamard lemma, also easy. Baker-Campbell-Hausdorff is a quite hard identity to derive, and not quite so hard, but easily also challenging is the exponential disentangling identity. But we're going to show you how that works in the lecture itself. All right, so let's get started. Our first identity is the Leibniz or product rule. And that says the commutator of A with the product of B and C is equal to B times the commutator of A with C plus A times the commutator of A with B times C. You can see you can think of this as moving the B, which is on the left, through the commutator to the left, and moving the C, which is on the right, through the commutator to the right. And if you think about sort of just sliding each of those operators out to the left or the right, depending upon the order that they appear in the product, that is the way that you can remember what this commutation relation is. How do we prove it? Well, we just use the add zero trick. So let's start off with writing down what the commutator of A with BC is. It's ABC minus BCA, and then we add zero. Now, as always with the add zero trick, which is doing nothing, you're just adding zero to your expression, you have to pick the right add zero to add. And in this case, our add zero is going to be minus BAC plus BAC. You can see that's, of course, zero because I'm adding and subtracting the same product of operators. But by doing that, I can now regroup. And when I regroup, you see I'm going to get AB minus BA times C plus B times AC minus CA. Of course, those are just the commutators. So I get the commutator of A with B times C plus B times the commutator of A with C, and that's it. We've just derived it. Now, it's called the Leibniz rule because it acts in many respects like a differentiation of a product rule, where the single operator in the commutator is acting kind of like a derivative, and the product operator is acting like the product of functions, and the only thing you have to really keep track of is the order of the operators. Now, it has other forms as well, such as commutator of the product of AB with C. And again, you just do the same thing. Move the thing that's on the left out to the left, move the thing that's on the right out to the right. So it's A times the commutator of B with C plus the commutator of A with C times B. You can go ahead and check that on your own if you like. Another related identity to this is the so-called Jacobi identity, which says that the commutator of A with the commutator of B with C plus the commutator of B with the commutator of C with A plus the commutator of C with the commutator of A with B. Those 3 terms have those 3 operators, A, B, and C, cyclically permuted in the 3 different expressions. The sum of all those guys is equal to 0. Now, personally, I don't find that this identity, this Jacobi identity, is particularly incredibly useful. There are a couple of occasions where it does come in handy and it is useful to use the identity, but often I find I never need it. So I don't view this, even though it's mentioned in many, many textbooks, I don't view this as one of the really critically important identities in quantum mechanics. Now, to prove it, you just have to write it out. So the first term, commutator of A with BC, is A times the commutator of B with C minus commutator of B with C times A. And so similarly for the other 2 terms, you then expand the commutator in each of the terms, and you get this big mess. I'm not going to write it out for you, but I'm going to carefully point out the cancellation of some of the terms. So let's look at our first term, ABC. If we start looking through the terms, we see that there's another ABC. The second to last term is minus ABC. So you see those terms will cancel. Let's look at minus ACB. We're looking for another ACB. And sure enough, the second term on the second line is plus ACB. So those 2 guys cancel. Let's look at minus BCA. Minus BCA, I just have to go 2 terms after that, I get a plus BCA, so that cancels. And you can go through and work through every single term, and you'll see every term that appears with a plus sign has another term that appears with a minus sign that matches it and cancels it. And so the net effect is that the whole sum is equal to 0. All right, we're next going to talk about the Hadamard lemma. I find this is something that isn't quite so well known by students of quantum mechanics, even graduate students at your stage. So if you've never seen it before, you're going to see it now. We're going to be using this operator a lot. So it is really important that you know and remember it, but really even more important than that is that you know how to use it. So what the Hadamard lemma says is that e to the a acting on the left of b and then multiplied by e to the minus a on the right is equal to a power series that's an infinite power series. B plus the commutator of a with b plus 1 over 2 factorial the commutator of a with the commutator of a with b. The next term would be plus 1 over 3 factorial the nested commutator of a with the nested commutator of a with the commutator of a with b, and so forth. We write that generally as the sum n equals 0 to infinity of an n-fold nested commutator where all of the nestings are a operators until the last one, which is the commutator of a with b, and then multiplied by 1 over n factorial. So to prove it, we generalize the formula to look at f of x, which is e to the xa b e to the minus xa, and then we just work out a Taylor series expansion. So first set x equals 0. That's obviously equal to b. Now let's take the first derivative of that. When I take the derivative of e to the xa, that pulls an a out. I can pull that out either to the left of the e to the xa factor or to the right of the e to the xa factor because it commutes with e to the xa. So that operator a can appear on either side, either to the left or to the right. I've written it here to the left of e to the xa, and then when I calculate the derivative of the second term, I'll get a minus a, and that a can appear either to the left or to the right. Now, what we're going to do is we're going to set x equal to 0 because we're trying to evaluate this derivative at x equals 0. But once I do that, you see e to the xa b e to the minus xa just becomes b. And so I'm left with ab minus ba, and that indeed is a commutator of a with b. Now let's do the second derivative. The second derivative, you can pretty much convince yourself, is equal to a times the first derivative at 0 minus the first derivative at 0 times a on the right. Please look very carefully at the way in which we calculate derivatives to verify for yourself that that is the way that you can write this. Now, plugging in what f prime of 0 is, you find that that's equal to the commutator of a with the commutator of a with b. All right, so now to get the general form, we're going to assume and do an induction proof that the nth derivative is equal to the nth fold nested commutator. And then because fn plus 1 evaluated at 0 is equal to a times f of n at 0 minus f of n at 0 times a, using exactly that same derivation that we just did above, you can see that that will become the n plus 1 fold nested commutator, and that then proves the expansion. We finally set x equal to 1 in the expansion, and that gives us the proof. Now, the proof is assuming that that Taylor series expansion of the operators does converge, and we are going to make that assumption that that converges. I can see that there is a typo in this. I seem to have dropped the 1 over n factorial in this expression, so I will correct that in the notes, but just remember that the final expression is sum n equals 0 to infinity, the n-fold nested commutator with all a's, and then the last commutator being a commutator of a with b in the innermost part of the nested commutator, and then it's multiplied by 1 over n factorial. All right, now the Braiding identity is even more powerful, and it comes from the fact that when I do a Hadamard transformation on a power of an operator, that is the same as the Hadamard transformation of the operator raised to a power. And to see that, what we do is we just take b to the n and we write it out as a product of b times b times b times b n times. And then in between any two b factors, we multiply by 1 in the form of e to the minus a times e to the a. And we can insert that in between each of the b factors, starting from the left and going to the right. And you see what we have then is we have n triples that are of the form e to the a, b, e to the minus a. And that means that that expression, e to the a, b to the n, e to the minus a, can be written as e to the a, b, e to the minus a raised to the nth power. Okay? What does that mean? Well, that means that I can then take any function of an operator, f of b, that can be written as a power series, sum over n, c to the n, b to the n, and then e to the a, f of b, e to the minus a will just be equal to the sum over n, c to the n, e to the a, b to the n, e to the minus a, and that will equal the sum over n, c to the n, e to the a, b, e to the minus a raised to the nth power I hope you can see where we're going with this. I'm going to now reveal what it is that we get. That's just f of e to the a, b, e to the minus a. So the e to the a, e to the minus a goes into the argument of the function. And now all we do is we replace the argument of the function by the Hadamard lemma, which replaces it by the sum n equals 0 to infinity, 1 over n factorial, the sum of the n-fold nested commutators of a with b. And this relationship where we've put that Hadamard lemma into the argument of the function is called the Braiding relation. It's a very powerful relation. It's sort of a very similar relation to the Hadamard lemma itself. We don't make it out as another different one of our 5 critical operator identities. It's sort of a corollary to the Hadamard lemma. All right, on to the next one. The exponential reordering identity is most powerful in the simple cases that I'm going to show you about. It is also a corollary of the exponential of the Hadamard lemma, but it is sufficiently different that I want to actually call it out as a separate one of the big 5 operator identities. So here we have a situation where we have 2 operator products, e to the a times e to the b, and I want to interchange the places and make it equal to something on the left-hand side times e to the a. If you like, I'd like to move the e to the a operator to the right through e to the b. And of course, we know we can't just trivially do this when a and b don't commute, but we can actually work it out with braiding. So we start from the braiding relation. E to the a, e to the b, e to the minus a is equal to e to the a, b, e to the minus a. And then I use Hadamard to get it to be e to the b plus commutator of a with b plus 1/2 double commutator of a with the commutator of a with b, and so forth. You can see all I've done here is I've taken f of b in the braiding relation and replaced it by e to the b. And now what we do is we multiply both sides by e to the a on the right. You're going to see on the left-hand side of the equality, I'll have e to the minus a times e to the a. That equals 1, and I get rid of it. So I'm left on the left-hand side with e to the a times e to the b. And on the right-hand side, I have e to the b plus commutator of a with b plus 1/2 the double nested commutator and so forth times e to the a. So I have achieved my exponential reordering. So if you like, when you move the a operator through the b operator, you have to do a Hadamard on the b operator in the argument of the function when you move it through. Now, in general, this is a complicated mess, but there are a couple of times where it works out to be very simple. The simplest situation is when the second nested commutator of a with the commutator of a with b is equal to 0. This would happen, for example, if a is equal to x operator and b is equal to the p operator. Commutator of x with p is ih bar. That then commutes with x, so that twofold nested commutator is equal to 0. And then what we get is a much simpler expression. E to the a, e to the b equals e to the b plus the commutator of a with b times e to the a. Now, if the commutator of b with the commutator of a with b is also equal to 0, which is true in the example I gave with a equals x and b equals p, then you can remove that exponential factor because it commutes with e to the b. You can factorize that exponential, and you'll get e to the commutator of a with b times e to the b times e to the a. Okay? That is a very powerful identity. It comes up often, and it is something that is well worth remembering. Okay? We're now ready to get on to our 4th major identity, which is called the Baker-Campbell-Hausdorff identity. It asks a question that is kind of halfway between the exponential reordering identity. It wants to take e to the a, e to the b, and write it just as e to everything in one exponential. Now, it turns out that this is actually much harder to work out. In fact, it leads to an infinite series of commutators, just like the Hadamard lemma, but even the coefficients of those nested commutators are not known, and even all of the terms that appear in the nested commutators are not known a priori. So it's a very complex expression. So as a warm-up, we're going to work with what is called the Weil form of the BCH identity. And in the Weil form, that occurs when the commutator of a with b commutes with a and b. That's the example we were just talking about. Then it's very simple to do this derivation. We simply construct a function f of lambda, which is equal to e to the minus lambda a, e to the lambda a plus b, e to the minus lambda b. And we're going to just take the derivative of that function. you notice that I can pull out a minus a that can sit either to the left of the e to the minus lambda a or to the right of the e to the minus lambda a. I will have a term that has an a plus b that comes out. That can appear to the left of the e to the lambda a plus b or to the right. And I will have a minus b. Again, the minus b can appear either to the left of e to the minus lambda b or to the right of e to the minus lambda b. So what we're going to do is I'm going to take that minus a and I'm going to move it to the left hand, to the right hand side. That's going to cancel with the a to the a plus b and just leave me with a b there. And then I'm going to take that b e to the lambda a plus b and I'm going to rewrite it using the Hadamard identity. I'm going to multiply by 1 on the left-hand side. You see I have a e to the lambda a plus b, e to the minus lambda a plus b that I'm multiplying by. That's just equal to 1. Even with operators, be sure you understand that. And you see now I have in the last 3 terms are e to the minus lambda a plus b, b e to the lambda a plus b. That's in the Hadamard form. So I can rewrite that triple product. So I still have my factor e to the lambda a plus b to the left-hand side. I can just rewrite that expression as b minus lambda commutator of a plus b with b plus lambda squared over 2 commutator of a plus b with the commutator of a plus b with b and so forth. And you see the first commutator is going to give me minus lambda commutator of a with b, but the second term is going to equal 0 because a commutes with the commutator of a with b, as does b. So that summation, the Hadamard lemma, truncates after just 2 terms, and that allows me to then take that expression that has the b e to the lambda a plus b and move the b to the right-hand side by adding this, by subtracting this commutator. So what we find now, that commutator can then be moved out because it commutes with a and it commutes with b and it commutes with a plus b. So the derivative of f with respect to lambda is minus lambda commutator of a with b times f of lambda, and there's nothing else left because the b, once I've moved the b to the right, it cancels with the minus b that's coming from the last term in the derivative. And then I'm just left with the commutator term. And because the commutator commutes with all the other terms, I can pull it out of those exponentials and recognize that the product of the 3 exponentials I have is just f of lambda. And now I can just integrate this. If I integrate this, I find f of lambda is equal to e to the minus lambda squared over 2 times the commutator of a with b times whatever f is when lambda equals 0. Well, f when lambda equals 0 is fairly easy to work out. F of lambda equals 0 is just equal to 1 because when I set lambda equals 0, e to the minus lambda a is 0, is 1, e to the lambda a plus b is 1, and e to the minus lambda b is equal to 1. So f of lambda is just equal to e to the minus lambda squared over 2 commutator of a with b. So we've determined this equation here. E to the minus lambda squared over 2 commutator of a with b is e to the minus lambda a, e to the lambda a plus b, e to the minus lambda b. Pretty cool. It kind of looks like something that is kind of like a Hadamard lemma, but it's e to the minus lambda a and e to the minus lambda b on the left and on the right. So it's not really a Hadamard lemma. Now, we just multiply on the left by e to the lambda a and on the right by e to the lambda b. And then because the term in the middle, the e to the minus lambda squared over 2 commutator of a with b, that commutes with everything, I can multiply by e to the lambda squared over 2 times commutator of a with b and bring it onto the onto the right-hand side. I can even bring it into the exponent because it commutes with a plus b. And I get our final result. E to the lambda a, e to the lambda b is e to the lambda a plus b plus lambda squared over 2 commutator of a with b. Now I'm going to pick the special lambda value that I want to pick in order to make this work. I pick lambda equals 1, and I get e to the a, e to the b is equal to e to the a plus b plus 1/2 commutator of a with b. This is called the Weil form of the Baker-Campbell-Hausdorff identity. It holds when the nested commutator of a with the commutator of a with b is equal to the nested commutator of b with the commutator of a with b is equal to 0. This is the easy case of BCH, and it's the version that most people know. Now I'm going to spend some time, and it's going to be a fair amount of time, working out the general case. If you feel like you need a break, this is a good time to have a break. And before we get started with our full derivation, we actually need another identity, we're going to look at the derivative with respect to x of an operator a of x, and my claim is that is equal to the integral from 0 to 1 dy e to the 1 minus y a of x d by dx a of x e to the y a of x. This looks very weird, but it takes this form, and you have to be very careful with how you work this out, because in general, if I have an operator a of x, then dA dx does not necessarily commute with a of x. Okay, let's think of an example. Think of an operator, I'd better use lambda. Let's think of an operator lambda times x plus p. Okay, if I take the derivative with respect to lambda, I get the x operator. The x operator, which is dA d lambda, does not commute with a of x because a of x, or a of lambda, because a of lambda has a p operator in it. And in general, if I have some operator that's a function of some parameter, it does not commute with its derivative. Okay? Now, d by dx of e to the ax is simply the derivative with respect to the power series. So 1 plus a of x plus 1/2 a squared of x plus 1/6 a cubed of x and so forth. But now when I take the derivative, I have to be very careful to use the chain rule and not move any non-commuting operators past each other. So the derivative of 1 is equal to 0. That term is gone. Derivative of a is just a prime. The derivative of 1/2 a squared is 1/2 a prime a plus a prime. I have to first I have to write a squared as a times a and then use the product rule. And I'll get a derivative of the first term in the multiplication and a derivative of the second term in the multiplication. And I can't simplify that and write that as twice a prime a, because a does not necessarily commute with a prime. Now, similarly, if I calculate a cubed, I'm going to get 3 terms. I'm going to get a prime with a squared. I'm going to get a prime a, and I'm going to get a squared times a prime, and so forth. It's very easy to work this out for any order of a to the n. It just is a long expression. There always are n terms in it, and it just involves taking the derivative and putting it in each place within that product of a squared operators that you have. So as I said before, we'll have m powers of a, we'll have an a prime, and then n minus m minus 1 powers of a, and it'll be a sum of all of those terms, and then it'll be divided by n factorial, and we can write that as a summation, sum n equals 0 to infinity, sum m equals 0 to infinity, of 1 over n plus m plus 1 factorial, a to the n, a prime, a to the m. Okay, so I've done a little bit of changing. You notice that it's 1 over n plus m plus 1 factorial because I've rewritten that first term as a to the n instead of writing it as a to the m. And I've rewritten the second power as a to the m as opposed to n minus m minus 1. This is done because it just makes life a lot easier when we're doing this expression. And the key thing here is that this expression is correct when I don't restrict those exponents to be, say, n plus m is equal to some integer, but you can quickly recognize that you get contributions when n goes from 0 to infinity and freely when m goes from 0 to infinity. And writing it in this form is very important in deriving the identity that we want to derive. So this is a non-trivial thing that has been written here, and if you're having any problem with understanding how that works, this might be a good thing to bring up when we have our live session. But if you're comfortable with it, just sit down, think about it carefully, write it down, and you should be able to verify that when I look at the sum over all of the terms in the power series expansion of the exponential, I can rewrite that derivative of the exponential in this form. Okay, now we're going to expand each term in the integrand. So we're now going to work backwards from the formula that we derived. So we first have to calculate that first integral. We have an integral from 0 to 1 dy. It was of e to the 1 minus ya, and then we had an e to the ya. So we're going to just calculate the power series expansions of e to the 1 minus ya. That's going to be sum n equals 0 to infinity, 1 minus y raised to the nth power, a raised to the nth power divided by n factorial. I have my a hat prime, and then I have the sum m equals 0 to infinity, y to the m over m factorial times a to the m. Now, I can move the integral and all of those numerical factors that depend just on y all the way to the right-hand side. I get an integral from 0 to 1 dy, 1 minus y to the n times y to the m. You might not have seen this before, but this is a very famous function. This is called a beta function. It actually holds for even complex valued exponents, but here our exponents are integers. And it turns out that that is just equal to n factorial times n factorial divided by n plus m plus 1 factorial. So that's all that that integral is equal to. When I collect the rest of the terms from the summation, I have a sum n equals 0 to infinity, sum m equals 0 to infinity, a to the n, a prime, a to the m divided by n factorial times n factorial. You see the n factorial and n factorial terms will cancel, m factorial and m factorial will cancel, and I'm left with the form that we had before, that I had said you get by just differentiating the power series. So we have just proven that the derivative with respect to x of e to the a is equal to integral 0 to 1 dy, e to the 1 minus y times a prime, e to the y times a. Now our next step is we're going to multiply on the left by e to the a. So we're going to get e to the a d by dx e to the a is equal to the integral from 0 to 1 dy, e to the y now, e to the minus y a prime, e to the y a. I'm sorry, I'm pretty sure this should be an a, e to the minus a I'm multiplying by in order to get this to simplify. I'm sorry, that is a typo there. We're multiplying on the left by e to the minus a. And so multiplying by e to the minus a, I get a d by dx. I will cancel that. The e to the 1 minus ya will just become e to the minus ya. Now we can recognize that we have a e to the minus ya, a prime, e to the ya. That's a Hadamard. I can expand that in a Hadamard expansion. A prime minus y, commutator of a with a prime, plus y squared over 2, double nested commutator of a with a prime, and so forth. We can then just write out what those things are. I'm sorry, we can actually do that integral. Integral from 0 to 1 of y is just equal to 1/2. Integral of y squared is just equal to 1/3, and so forth. You can see I'm starting to get things that are going to look like 1 over n factorials for those coefficients. Okay, now to get to the BCH, what we're going to do is, so that is the lemma, that is the thing that we're going to be using in just a moment. So we'll get back to that in a moment. Now we're going to be starting again on a new operator identity. We're going to look at e to the xa, e to the xb, and we want that to be equal to e to the g of x. You notice we're going to be setting x equals 1 at the end, but we're going to expand that g of x in a power series, x times g1 plus x squared times g2 plus x cubed times g3 and so forth. We'll find that that becomes very handy having it in that form. And what we're going to do is we're going to multiply this expression. Let's see, I'm multiplying first on the right by e to the minus xb, and then on the right by e to the minus xa, and then on the right by e to the minus g of x, and then on the left with e to the minus g of x. You see what we're going to get is we're going to get e to the minus xb, e to the minus xa is equal to e to the minus g of x. That's in some sense just the inverse relationship. When I look at the inverse of two matrices, I have to invert the order of the two matrices. The same is true with operators. That's why it's e to the minus xb, e to the minus xa on the right-hand side. Now I'm going to multiply on the right both expressions by d by dx of e to the g. But e to the g I'm going to write as e to the xa, e to the xb on the left-hand side. I'm going to just write it as e to the g on the right-hand side. Now, the left-hand side can be evaluated directly because d by dx, I pull an a out when the derivative hits the e to the xa, and I pull a b out when it hits the e to the xb. I'm going to pull the a out all the way to the left. I'm going to pull a b out all the way to the right. You see that I'm going to have in the a term, I'm going to have e to the minus xa, a e to the xa. Well, because a commutes with a, that the e to the xa and e to the minus xa just commutes through it, and the e to the minus xa cancels with the e to the minus xb. I have then an e to the minus xb, a e to the xb. That is going to be a term that I'm going to keep. And then you can see the other term where the b is pulled all the way out to the right. I just get a cancellation, e to the minus xa with e to the xa, and then an e to the minus xb with the e to the xb, and I'm just left with the b term. So what I have is I have b plus this Hadamard on the a. Now notice the Hadamard has a minus xb, so I have to be careful about the sign, but when I evaluate that Hadamard, I'll get b plus a minus x commutator of b with a plus x squared double nested commutator of b with the commutator of b with a, and so forth. Now, but using the identity we had before, e to the minus g of x d by dx e to the g of x, that's just equal to g prime plus 1/2 commutator of g prime with g plus 1/6 double nested commutator of the commutator of g prime with g, commutator with g, and so forth, and that becomes an infinite series that keeps on going. We're now going to use the power series for g of x, expressing it in terms of xg1 plus x squared g2 plus x cubed g3, and we're going to now calculate the derivatives. Derivative of g prime is just going to equal g1 plus 2x g2 plus 3x squared g3, and so forth. Having g prime, I can now calculate 1/2 the commutator of g prime with g. I have two power series I have to substitute in. So this requires, collecting lots of terms and other things like that. The first term I have is a commutator of g1 with x times g1, but g1 commutes with itself, so that term is 0. The first non-zero term I have will be a commutator of g1 with x squared g2 plus a 2x g2 commutator with x g1. And you see that's going to give me an x squared g1 g2 plus a 2x squared g2 g1. Reordering those in terms of the commutator of g1 with g2 is going to give me a minus x squared times commutator of g1 with g2. It looks like I decided to write it as plus commutator of g2 with g1. So it's plus 1/2 x squared commutator of g2 with g1. I then look at the x cubed terms. You have to carefully look at all possible x cubed terms, the g1 with the x cubed g3, the 2x g2 with the x squared g2, but of course g2 commutes with itself, so that's 0, and then the 3x squared g3 with the x g1. Those are all the cubic terms. So then you collect those as well, and you can see that you start getting an expansion, 1/2 x squared commutator of g2 with g1 plus 3x cubed commutator of g3 with g1, and so forth. And then you can work out the first double nested commutator, 1/6 commutator of g prime with g, commutator with g. Okay, go ahead and work that out. I'm not going to say it all through you, but it comes out as x cubed over 6, double nested commutator, commutator of g1 with g2, commutator with g1. And so we now have a power series expansion in x for e to the minus gx d by dx e to the gx. It's equal to g1 plus 2x g2 plus 3x squared g3 plus x squared over 2 commutator of g2 with g1 plus order x cubed. Okay, but doing the work that we had on the right-hand side, which is shown for you in the middle of the page here, we have that is also equal to a plus b plus x commutator of a with b plus x squared over 2 commutator, nested commutator of b with commutator of b with a, and so forth. So now we equate terms according to powers of x. So g1 must equal a plus b. g2 must equal 1/2 commutator of a with b. 3g3 plus 1/2 the commutator of g2 with g1 is equal to 1/2 the commutator of b with the commutator of b with a. Now to calculate this, I got to substitute in what g2 and g1 are and rearrange. Let me move that 1/2 commutator of g2, g1 over to the right-hand side and divide the whole thing by 3. So I'll get 1/6 commutator of b with commutator of b with a minus 1/6 the commutator of g2 with g1. g2 is equal to 1/2 commutator of a with b, and g1 is equal to a plus b. So now you have to do a little bit of algebra and work things out, and you find that g3 is equal to 1/12 the nested commutator of b with the commutator of b with a plus 1/12 the nested commutator of a with the commutator of a with b. You really have to sit down and carefully go through that algebra. Make sure you pause this and go ahead and do that, but that's what you get. So we've now actually gotten explicit expressions for g1, g2, and g3. We're going to set x equals 1, and then what we find is our expression is going to give us e to the a, e to the b equals e to the g of x equals 1. That just equals e to the g1 plus g2 plus g3 and so forth. We just plug in what that is. It's e to the a plus b, that's g1, plus 1/2 commutator of a with b, that's g2, plus 1/12 nested commutator of a with commutator of a with b, plus 1/12 nested commutator of b with commutator of b with a, and so forth. And that is the BCH identity. And you can see that in principle, we have a algorithm to calculate all higher order terms, but you can also see it gets very, very painful in order to do that. Okay? So you now are in a very select group of people. Very few people who study quantum mechanics have ever actually derived the next term in the BCH series. And you actually can follow this procedure and derive the next term after that as well. It just starts to get kind of complicated. You want to go further than that. All right, so now we're going to just talk about our fifth identity. That's the exponential disentangling identity that I introduced you to in the first lecture using the Pauli spin operators. The thing that is a miracle about this is it uses a theorem from Lie algebra. And the theorem from Lie algebra, which we're not going to prove, I'm going to just tell you what it is. It says any identity expressed in terms of exponentials of the generators of a Lie algebra that is proved for one faithful representation holds for all representations. Now, the identity we worked out last time was exponential of I times 2v dot s over h bar using the spin 1/2 operators, or using spin operators. S equals exponential alpha 2s plus over h bar, raising operator, exponential beta 2sz over h bar, exponential gamma 2s minus over h bar, where alpha, beta, and gamma were determined as functions of the v's. This actually holds for any angular momentum representation. So I can substitute those s operators by l operators. I can substitute in j operators. Any angular momentum operator I want, I can substitute in. And that identity as an operator identity holds. This is really amazingly powerful. We just proved something about Pauli spin matrices by doing factorization of Pauli spin matrices and using the fact that the exponential of Pauli spin matrices can be exactly computed. And it then holds for all possible operators that satisfy the angular momentum commutator relations. We're going to use this again many times in the class. Now, I want to point out, to give you a sense of how miraculous this identity is, the formula that we have for the exponential of v dot s, expressed as you get with the Pauli representation, that doesn't hold as an operator relation for exponential of v dot s. I don't know what that exponential is. And similarly, I don't have a closed form expression for it, what exponential of alpha 2s plus over h bar is, when s plus is an operator. And I don't know what it is for well, actually, I probably can work it out for exponential of 2sz over h bar, but even there, I'm not completely sure I know how to do it, and so forth. So, but nevertheless, as an operator identity, this thing holds, and it was proved by doing that expression with the Pauli operators. That's just really cool, okay? If you don't believe that that's really cool, you should be just saying to yourself, wow, I might not be able to follow all of that. I might have to pause this and go back. But that just sounds really cool that you can derive such a powerful operator identity just by factorizing and taking exponentials of 2x2 matrices. Okay? All right, that brings us to the end of lecture 2. And next up will be lecture 3. And I will probably see you in class before you start looking at lecture 3. So be sure to save all questions that you might have about the lectures for class. Please take notes. I hope you are still following the advice that I told you to do, which is to take notes as you watch the video, and to also, a day or two after you've watched the video and taken notes, go and rewatch the video at least once, which means after you've finished watching this video, if you haven't done it already, you should go back and rewatch video 1. Okay? We'll see you in video 3.